Continuing on with class 23, here's another problem. For an example, this is problem 673 of the book. We have 1 kilogram of water again, 500 degrees Celsius, and we have another kilogram of saturated water vapor, right? Both of them are at 200 kilopascals, and they're mixed in a constant pressure and adiabatic process. Find the final temperature and the entropy generation for this process. So this is a little bit of a different one. So it's not like we're really covering or thinking our way through a problem and not necessarily trying to come up with, here is a problem that you will always do. No, we're just trying to see if we could use these concepts. And I made a pretty good mess of my page as I was doing this. So I will try to be neater in here. So I'm decided to call, we have two sets of masses. Let's call one of them A and one of them B to try to keep them straight. So the mass A, so we go MA is equal to 1 kilogram. Doesn't really make much sense, but we'll do it anyway. A1 is equal to 500 degrees Celsius, and they said both of them are at so this PA1, it's 200 kilopascals. And then B, we have MB, 1 kilogram. And we don't know the temperature of this one, but we know that I was about to say temperature. We know the pressure. We know that it's 20 kilopascals and that it's a saturated water vapor. So PB1 is also 200 kilopascals. We'll go take a look at that in the steam tables and come up with this. We know that these two things are going to get mixed together at a constant pressure. Well, they're 200 already, both 200 kilopascals, so that's the pressure. And adiabatic, right? So what we know about that, let me see if I can say this right. It's an adiabatic process, but that doesn't mean that we don't generate, and that always bothers me. Okay, no. Okay, so here is an instance where it does not isentropic. It's adiabatic, but not isentropic. Yes. Okay, good. That means there's no heat, no Q. Right? So Q is equal to 0. Q between during this process is 0, and P is constant. All right. So we've set up a scenario where we have adiabatic but not isentropic. So let's look up these properties. That's the first thing, just to get this out of the way. If we look up into, first off, let's go to superheated. I'm pretty sure that the 500 degrees Celsius and 200 kPa, right here is 200 kPa, so let's zoom in on that. There's 200, and sure enough, 5 right there. Okay, so here are the properties that we want for that first one. I don't know if we need to write all those down. I wish I'd left some space for myself, so once again, I didn't organize like I wanted to. But let's go. The things I want, I think I need internal energy. I don't think I need I don't need a specific volume. And I may or may not need enthalpy. I think I need enthalpy, sorry. All right, so we'll have HA1 is going to be 3,487 kilojoules per kilogram. And we also want the entropy. So the entropy SA1 is 8.5132 kilojoules per kilogram degree Kelvin. Anything else I want from this? I don't think so. All right, so the other, so the B, if you'll recall, B is going to be at this pressure, but it's going to be a saturated water vapor, right? So let's come back up to this one right here. And we need the pressure. All right, so we need the B.1.2, and let's see, that's going to be at 200, right? 200 kilopascals. All right, so if we cared, we might get that it's 120 degrees is what the, let's see, so B Tsat, if I'm looking at this right, 120.23 degrees Celsius. And I don't think we need that. We need 200 here. And we need, it's a gas, is a liquid, is a mixed, is a vapor. So we need, yes, that, and need this. Boom. So HB1 is equal to 2,706.63 kilojoules per kilogram, and SB1 is 7.1271 kilojoules per kilogram degree Kelvin. All right, coming back onto here. See, that thing's gonna start up slowly again because it's being a jerk. 701. Okay. So we have two things in there mixing, so we might want to use the conservation of mass. In fact, we kind of have to, and say the mass after these two things happen is going to be MA plus MB, and that's really hard to do, right? 1 plus 1, and spoiler alert, 2. We have the conservation of energy. Not a coup, it's a co. The conservation of energy says that we're going to have U2 minus plus U2 minus U1 equal to Q1 to 2 minus work 1 to 2. And so this is going to be 0 right there because it's adiabatic, right? And also we might note, might we? Sure. That work is going to be from 1 to 2 is the integral of P dV, but this since it's constant, it's going to be P times V2 minus V1. And we're going to use that idea here to say that, and we have, by the way, this is as if we have a single mass going on, right? Or single mass, but we have in state 2 we have two masses. In state 1, no, excuse me, state 2 we have a single mass. State 1 we have two masses, right? They combine with each other. So we need to look back into that. So if we were going to try to put this thing together, what we would say, we go like M2 times U2, right, is going to be, trying to think, I didn't plan ahead for this right here. So I'm going to say, so that's going to be this guy, minus MA UA1 minus MB UB1, right? It's going to be equal to, and then over here, let's say that we had M, all right, so I'm going to have negative right there. Excuse this mess. Is that going to be true? Sure. MA, and then, okay, so we need to go work. I'm trying to think how I'm gonna do this. They just jumped to this conclusion, so I want to try to do this in a more logical fashion. And I also want to keep the signs correct. So I said, so the change in work from 1 to 2. All right, so I'm going to go M2 times P, and we'll go V2. All right, so that's going to be the P V2, and they're going to go plus MA times P VA1 plus M. Okay, yeah, that'll be fine. BP. Sorry, I'm also making a mess here. B1. All right, so what we could do now is come back onto the other side. M2 U2. But we're going to bring this on the other side. Going to be plus PV2 is going to be equal to MA times UA1 and then plus PVA1 plus MB UB1 plus PVB1. Now this right here is H2. This right here is the definition of HA1, and that's the definition of HA2. All right, so that's why we're using enthalpy, make your life a little easier. We could test this out too if we wanted to, but that's just sort of a little bit of a shortcut. And so what we could have here is going to have 2 times H2. It's going to be equal to 1 times HA1, which was 3,487, plus 1 times HB1, which is 2,706.63 or whatever the hell it is. Okay, so we can find what H2 is. H2 is 3,096.8 kilojoules per kilogram. And now we can look up at P2 equals 200 kilopascals. We can search for this entropy. So let's go back and search for that entropy. And so let's assume that it's going to be superheated. I think that's a fair statement because one of the things was began superheated, and the other was just on the verge of being superheated. So you could conclude, yeah, it's probably going to be superheated. So let's see. I think I had that already. I should get rid of it. So we have 200 kilopascals, and we need 3,096. So here's 2,000. Let's see, that's H, right? 2,000. We need 3,096. So we're going to be between here and here, between 300 and 400. So there's 300 degrees and 400 degrees. So we would want to interpolate in between there, and also interpolate this, right? So interpolate two things. Find out what the temperature is, because they were asking, and then find out what the entropy is going to be. So I'm not going to bother interpolating right here, but let's see. I'll write this down just to keep it as if we did it. So interpolate. Come back. Interpolate table B.1.3. We find that T2 is going to be 312.2 degrees, and that S2 is going to be 7.9328 kilojoules per kilogram degree Kelvin. Now, if we go back to, I think I just went ahead and jumped to our ins and outs onto the thing. I think this is true. That we can go ahead and say in these terms. I'm trying to reconcile the trying to reconcile the sign convention. 1 second here. Let me pause. All right, so coming back to this main equation right here. This is equation 637. It's our main guy. Because we don't have any heat transfer right here, they're saying there's heat transfer. All we're going to find when we go to this, when they're asking for what is the generation thing, is just going to be 2 minus 1 right there. But of course, there's masses going on to here. So we will say from equation 637, which will go S2 minus S1 is equal to that del Q over T, and that T is like for the boundary right there. So we go plus S 1 to 2 gen. So we go S 1 to 2 gen. It's going to be M times S2 minus, well, M2 is going to be M A S A1 minus MB S B1. We have that, right? So we go 2 times 7.9328 minus 1, and SA1, remember, was 8.513. So 8.5132, and then minus, 1 times 7.1271. 7. Try to move this down. 7.1271. And so we should get the answer for here. Well, first off, here's one of our answers. We should write it at the end, but I'm not going to right now. S1 to 2 gen ends up equaling, let's see if I can get this out of my way, 0.225 kilojoules per kilogram degree. No, it should be just per degree Kelvin, right? Sure. Degree Kelvin. And so here's my, so we generate, so even what this says, or really kind of demonstrates, is that even though it is adiabatic, we could still have entropy. We could, so it's not like we're tied to, just because something is adiabatic doesn't make it reversible, and doesn't make it isentropic. So that was a good example. I'm happy I accidentally picked it. I wasn't sure. I didn't put a lot of thought into it, to tell you the truth. I think I probably did. So we're on to the next video.